Today I would like to talk about optimal sharing in social dilemmas. And this is a joint project with Manoj Stab, Valentin Hübner, Christian Hilde, and Kleshnina Chatterjee. So we started working on this project slightly over a year ago, so it's work in progress. So all the comments and questions are welcome. So I would like to open up with a quote. Equals should be treated equally and unequals unequally in proportion to relevant similarities and differences. According to Aristotle, this was the idea behind addressing inequality. And this will be probably the main message of this talk, and I will get into details more right now. So to briefly tell you how the talk is structured, I will first start with the motivation, and I'll talk about the model, and I'll just explain how we analyze the equilibria, and also show you how we address the evolutionary part of the model. And in this case, we did some simulations, and I'm sure it will be nice to see, but there's also an additional part that I will see if I have time. If we are good on time, then I will also tell you a bit more about heterogeneity for outside options, and I'll tell more about it. What does it mean later? And then I will conclude with implications of our results. So to motivate the study, I would like to talk about public goods. Say, if we are thinking about pure public goods, say parks in the city, then this is a pure public good. So anybody who goes to the park can benefit from it, and we cannot restrict to only the taxpayers to use this park. So anybody who wants to go there can go there, and everybody who goes equally receive the unequal share from this park. So they go and spend their time and enjoy. Whereas there's another social dilemma that can be seen as a public good, but it's more of a collective action problem. For instance, community gardens. So here the membership in the garden can be limited, and only members can benefit from the garden, and these members have to contribute, and the results of the garden, the production, is then allocated among the members. So in this problem, in this project that we study, we mostly focus on the second part, on the second type of the public good, where allocations can be controlled. So we can actually define and agree on the rule how the produced public good is shared among everybody. So usually in evolutionary games and in general in games, the approach is to look into pure public goods so that everybody gets the same share from the produced public good. However, we know that in nature, this is not always the rule that is used. So for instance, in lions, lioness actually do the hunt, but male lions are the ones who get the larger share and they eat first. And for instance, in cancer cells as well, if the public good is produced, those cells that produce, they develop mechanisms that help them to consume more of the public good that they produce. And those who do not produce it, they get the public good, but their consumption is lower. And similarly, in hunter-gatherer societies, the hunters who actually kill the prey, they usually obtain a larger share of the gain. And in the teamwork productions, in research teams or in companies, the credit can be shared unequally depending on the contributions or any other agreements that were made beforehand. So usually in the literature, there are sharing rules that considered. First is the egalitarian sharing. And usually it comes in, shows up in non-cooperative game theory. And of course, it's simple because one doesn't need to track how much who contributed. The sharing rule is straightforward and pretty obvious. Everybody gets the same share. And also these allocations are envy-free. And also the second rule is the proportional sharing. So say proportional to contributions, which is often considered in cooperative game theory setup. And there it's mostly a concern of the stability of coalitions. So there is no deviations happening within the coalitions. But both rules fail to fully reflect individual strategic incentives. So maybe there is another better way to share. So we would like to see into this and try to understand it a bit better. And if we survey the literature, we can find several facts. First is that inequality generally seem to make cooperation harder. And this happens often in the pure public good setup. So both experimentally and in models, if players are unequal, cooperation becomes hard to sustain. And if we are in cooperative games and we want to avoid coalition deviation and the game is linear, then it is optimal to share the profits proportionally to individual contributions. However, recently there was a paper that considered the cost, the repeated partnership between two players, and the costs of players were different in this game. And they showed that if this is the case and the costs are different, then the sharing rules should be unequal, and it doesn't necessarily need to reflect the sharing, the cost of the players. However, in this particular case, authors mostly focused on the effect of imperfect monitoring. So if there is some kind of stochasticity to the environment and not all the actions can be observed, and how this affects the sharing rule. And we would like to more focus on the effect of inequality and derive a more general observations about how inequality affects the sharing rule. And can we actually find a sharing rule that would be a mechanism that can help to sustain cooperation better? So to do so, we would like to construct a game, and this is a rather straightforward, simple game. It's an infinitely repeated public goods game. There are n players. At every time step, they get some endowment, and these endowments are unequal, so every player gets a different endowment. And they have to decide on how much to contribute to the public good, or how much to keep to themselves. And their contributions, depending on how much they contribute, are multiplied by some productivity factor, and these effective contributions are then summed up, and this is the public good that will be shared. And at every, and there is a continuation probability, so at every time step, there is a probability that the next round will happen with delta or 1 minus delta, that the game will end. So we're building on the model discussed in House et al. In their paper on social dilemmas among unequals. So before I go further into the model, I would like to talk a little bit more about one simplifying assumption that we make. So this assumption is made without loss of generality, so we normalize the endowments. We basically are only interested in the share of the total endowment that each player gets. So say there is a total of 1 and it's shared somehow among the players. So the summation of the endowment is 1, and this means that we can neatly represent any endowment distribution on a simplex. Say if we have 3 players, we can just construct a simplex, and then any point in the simplex will be the endowment distribution. So if it's in the middle of the simplex, then all players are equal. If it's on the boundary, then 1 player doesn't have the endowment at all, and only 2 players have the endowment. And if it's a vertex, then only 1 player has everything. And somewhere in the middle, that means that they're unequal and just 1 player has more, others have less. However, I would like to note here that we only, in the further, we only focus on the points that are in the middle of the simplex, or in the interior at least, not on the boundaries. Because whenever we're on the boundary, that means that we're just excluding 1 player from the game, and we're considering the game with less number of players. Whereas we would like to consider social dilemmas where the cooperation is needed from everybody. So we have 3 players, we need all 3 to sustain, to make the project happen. And then, so we're only interested in those endowments that are not 0. So this is key to all the figures that I will be showing further, because all the figures will be shown on these simplices. So that's why I'm explaining it right now. So to give coming back to the idea of the model, so now in the notation of the model, we have some players, they have different endowments, they contribute, and under equal sharing, say in 3 players, every player would get just 1/3 from the public good. And in proportional sharings, there would be some parameters, alphas, that will tell us how much each player gets, depending on their contributions. Or the third alternative is that there could be some other optimal sharing rule that we want to find, and we want to see if it exists and if it helps to understand the cooperation. So to motivate it with the example and see how inequality works in the sharing rules that are usually used in the literature, would like to first look into equal sharing. So it's the first column in the figure. So this is this endowment simplex, and the shaded area is the area where cooperation is an equilibrium for this given parameter set. So basically we have 3 players, and equal sharing can sustain cooperation only when players are relatively equal and there is no extreme inequality. So once there is an extreme inequality, cooperation breaks down. So when we talk about proportional sharing in our model, we can think about it in 2 ways. So first, we can think about it as proportional to absolute contributions, meaning that this would be proportional to their endowments. So this is the second column on the figure, and we can see that here the proportional to endowment sharing is a little bit less sensitive to inequality, and also the player 3 in this case has slightly higher productivity, and the feasibility of cooperation, this area, is extended towards the more productive player, meaning that if the more productive player is rich, then cooperation is more likely to be sustained. However, it is still, inequality still breaks cooperation, meaning that if least productive players get more endowment, then cooperation cannot be sustained. So in this case, there's still negative effect of inequality on the sustainability of cooperation. And the second way to think about proportional sharing rule in the model is proportional to their effective contributions. So there is this productivity factors that could also differ among players, and basically their contributions are now weighed by these productivity factors, and we share according to how much they contribute to the public good effectively. And in this case, the effect of inequality is quite the opposite to the effect of inequality in the proportional endowment sharing, because now it is harder for cooperation if more endowment goes to more productive player. And if more endowment goes to least productive players, then it gets better. Cooperation can be sustained. And yet still there is this extreme inequality cases where cooperation breaks down. So it is quite hard to make a general conclusion from all these rules for the effect of inequality exactly, because it's quite the sustainability of cooperation is quite sensitive to the exact rule we are picking. So the question is there a way to avoid this? Is there a way to look at it a bit more general? So to answer this question, we can go straight into the model. So we construct the utility function as a linear public goods game, but now instead of this sharing 1/n, as it would be considered in the egalitarian sharing, say, we use some fi, which would be corresponding to a share that player gets from the public good. So the first part of the summation is the share from the public good, and the second part is the endowment that they keep to themselves and they do not contribute to the public good production. And since it is an infinitely repeated game and there is a continuation probability, we can sum across all rounds and look into a total payoff for all players. So 2 notes I would like to make here. First is that we're interested in the full cooperation, because we would like to see if even for for which inequality cooperation can be sustained at full so that everybody contributes. So if there is a team production project that requires contribution from everybody, can we find a way to share it so that everybody is interested? And also, this also contributes to the idea that we want to look at social dilemmas. So basically in social dilemmas, it's socially optimal that everybody contributes. So we would like to find a rule that helps to sustain social optimal equilibrium. But it also means that there is individual incentives to free ride, because if there is no such incentives, then everybody will be just contributing and it will be trivially true that everybody contributes. So we want to keep this tension and see if we can overcome the individual incentives. So to find the rule, we would like to find a way to sustain cooperation. And in order to do so, we want to find the harshest punishment that can sustain cooperation in subgame perfect Nash equilibrium. So the most harshest punishment here would be that if somebody deviates, then everybody goes in full defection. So this is what is called Grimm's strategy. So if as long as there is cooperation, people cooperate, but once there is a deviation and defection, then everybody goes into full defection, and cooperation cannot be recovered from this point onwards. And because defection is a Nash equilibrium, this means that this punishment can sustain cooperation as a subgame under subgame perfect Nash equilibrium. So we compare the payoff from full cooperation to the deviation given the some rule F that we want to find. And we can rewrite this condition as the constraint on the shares that players have to get. So this inequality 1 gives us the constraint on the minimum share given parameters of the game that each player has to obtain. And it depends on the endowments, productivities, and the continuation probability. So if we, for instance, denote this by F star, this equality to this constraint, we can show that cooperation can be sustained even only if the summation of F stars is less or equal than 1. So basically, if the sharing rule that can sustain cooperation is feasible, because this is the requirement for feasibility, then we can find the rule that can sustain cooperation. And the game with this rule is still a social dilemma. So to demonstrate how this works, we can look into example, for instance, say all players now, assume all players now equal their productivities. And in the first column, we can see that for given productivity, the equal sharing only can sustain cooperation in one point, which is the exact middle of the simplex, which is corresponding to all players that equal in the endowments. And for the same parameters, optimal sharing can sustain cooperation for any endowment distribution. So basically, there exist rules that satisfy the condition for sustainability of cooperation. So we can find the rule that will help us to sustain it. And as we reduce the productivity of the game, the equal sharing fails to sustain cooperation, and the optimal sharing becomes harder in the middle of the simplex, where players are equal. And as we go further to the boundaries, as we go further to the corners of the simplex, the cooperation can be sustained. And we can demonstrate it a little bit further. So say now players are unequal in productivities, and on the left, there are two simplexes which correspond to the optimal sharing and the equal sharing in their feasibility of cooperation. And we can see that optimal sharing is better at, so that there exist rules that can sustain cooperation. And we can also plot this in 3 dimensions to see actually how this works. So this endowment simplex corresponding to the 0 is this constrained level of sum of F stars minus 1 equal to 0. And so basically the requirement is that cooperation can be sustained as long as these constraints are below the simplex. So if we're above the simplex, then the cooperation cannot be sustained. And equal sharing has these constraints coming from the top, and they can only sustain it in a small area, whereas there's this whole area underneath the simplex in blue, where we can see that there might exist a different sharing rule, and this rule can sustain cooperation much better. So, right, so one thing to note about this graph is that there is this distance between the surface of the constraints for cooperation and the simplex. And this distance tells us a little bit more about how easy it is to sustain cooperation. And when I say easy, it means that either there are rules that do not require grim punishment, that might be less strict punishment that can already sustain cooperation, or is that cooperation works for lower values of the continuation probability. So we can map this on our simplices, and now this heat map tells us how far the constrained area is from the simplex. So the darker the color gets, the larger the distance, and the lighter the color, the closer the constraints are from the simplex, and less rules we have to find from these constraints. And when the area is white, it means that the cooperation cannot be sustained for these parameter sets. And we can actually prove the exact effect of inequality given unequal sharing that satisfy this grim punishment, that for any productivities and continuation probability, there exists an endowment such that it allows for cooperation. So we can find a sharing rule that will sustain cooperation. And also, if we have given productivities and endowment, we can find a more unequal endowment such that cooperation is easier to sustain. And as I said, easier, meaning that it requires a lower delta, or it doesn't need this harsh punishment to be sustained. And more unequal endowment, when I say more unequal endowment, you might see it as, say, you take some endowment from the poorest player and you give it to the richest player, and this will be a more unequal endowment. So we go further to the corners and we make players more unequal. So the main message here is that inequality actually makes cooperation easier. So, which is quite counterintuitive, and it is in sharp contrast to the general predictions of the public goods problems. So now talking a little bit more about this distance. So I was talking that there might be different rules and so on and so forth. So what does it actually mean? So if we are, for instance, in the case where one player, player one, gets a larger endowment, so this corresponds to the area where the surface goes really down and becomes quite far from the simplex. So say we are in the endowment distribution that corresponds to the constraints minus 0.4. So what does it actually mean? It means that the shares that need to be distributed are only they only sum up to 0.4. So there is 40% to 0.6. So there's 60% that have to be distributed in a particular way. But there's also this 40% leftover that needs to be distributed somehow. So the question is, how can it be distributed? The answer is, it doesn't really matter. So as long as the 60% is distributed in a way that, according to the formula I showed you, to F stars, then the cooperation already can be sustained. However, of course, this means that there are then bargaining opportunities. So players can start bargain on how much they get out from the surplus. And this might be dangerous for cooperation because then again, we need to consider what kind of bargains there are and how players play it out. So instead, to reduce these tensions, what we could do is we could look at the rule that is in the limit of sustainability of cooperation. So the limit of sustainability of cooperation is such delta for which the lowest delta for which cooperation can be sustained. So if we define the sharing rule F star hat such that it is the sharing rule with delta minimum, so the minimum delta that is needed for cooperation, so for any larger delta, it will be no problem, and say this is where it is critical, then the summation of the sharing rule will be 1. So there will be no ambiguity. There will be no need to bargain and talk about how to distribute this surplus. And this sharing rule F star hat will be the one, if any rule works, this one does, because it works with the minimum delta required for the cooperation. And we can actually demonstrate this a little bit better with the plots. So we can plot the delta minimum for this example that we go throughout this talk. And this delta minimum is the surface on the top left. And we can see that this delta goes closer to 0 as we go further to the corner. So the when players become more unequal and one player gets larger endowment. And if we were to, if the patience of players corresponds to delta minimum, so if the actual continuation probability is greater than any of the delta minimum for any of the parameters, then cooperation can be sustained anywhere. So this is this left bottom corner of the figure where any endowment distribution can sustain full cooperation among players. But if players have patience lower than required, say if delta is equal 0.5, then it could be that there exists this infeasibility area again that we talked about that cannot sustain cooperation. But this will still, it works the same under this F star hat as before. So basically this F star hat rule with delta minimum, it reflects qualitatively the behavior of the constraints and it reduces the ambiguity of the surplus sharing. So it is a unique optimal sharing rule that can sustain cooperation in the limit. But of course, because delta minimum is determined by the shares and shares are determined by the delta minimum, the question is, how do we actually find it? So for 2 players, it might be rather easy or straightforward, but if you have 10 players, it might be not so straightforward anymore. So there is a way to write it out so that we can actually derive it analytically. So it comes from the meaning of the delta minimum itself. Basically, we need to find when cost of punishment for defection is exactly equal to the private benefit from defection. So this only happens at this delta minimum. And once delta grows, then cost of punishment overweighs the benefit from defection. And from this n equations, we can actually obtain a system that can directly tell us the delta minimum and F star. And you can see from this equation with phi matrix that directly that this is the eigenvalue of the matrix and F star hat is the corresponding eigenvector, where the entries of phi is given by this formula. So basically, if we know endowments and productivities, we can plug it into the matrix and we can find the eigenvalue and it will be delta minimum and the corresponding eigenvector will be the sharing rule that needs to be agreed on for the players. So now we know how to find the rule, we know its properties, we know how it reacts on inequality and what happens to it. So we would like to come back to where we started first, to comparison to other sharing rules. So how does it actually qualitatively compare to the classic sharing rules like egalitarian or proportional sharing? So can equal sharing be optimal? The answer is yes, but it's a rather non-generic case. So for instance, if all players' productivities are equal, then the only possibility for the equal sharing to be optimal is when endowments are also equal. Once there is any inequality, this condition breaks down and equal sharing is no longer optimal. The same goes for the sharing proportional to the endowment and sharing proportional to the effective contributions. So we can define the set of conditions for when it is possible that they coincide with the optimal sharing. If the players' productivities are unequal, so here it's already everywhere stated that endowment distributions are non-generic. What it means is that there might exist a set of points where this can happen, but it's not a continuum. It's not that it's generally true. So to provide some intuition behind it, we can just look into example and say a more simple example with only two players, where one player is player one is not very productive and player two is more productive than player one. And we just vary the endowment and we see how the sharing reacts on the inequality. So equal sharing is just a dashed line that just 1/2 each player gets the same. And if we share according to endowments, then this green line is just a 45-degree line and it doesn't react on the productivities at all. It just tells us that the richer player gets more, the poorer player gets less. And once we share according to the effective contributions, this is the orange line that becomes, so the share of the player that is less productive becomes slightly less, and the share of the more productive player becomes slightly more. But in the corner cases where one player has almost everything, qualitatively, it behaves different, it behaves the same as the proportional to endowment sharing. But the optimal sharing, on the other hand, behaves differently than any of the rule considered before. So in this case, it's for player one, it's the pink line, and for player two, it's the blue line. So here we can see that if least productive player is rich, they get a rather big share of the public good, given that they're not productive. And if the rich player, if the productive player gets more endowment, their share that they need to be guaranteed is actually smaller in comparison to their effective contribution. So this effect might seem as unfair because less productive players actually have to be guaranteed larger shares, and it might seem as not a straightforward conclusion. And here it is dictated to provide the intuition, it is dictated by the individual strategic incentives. So here, the richest player, if they deviate, then contributions drop significantly. And then they gain less from deviations, so they lose quite a bit. And the poorer player, the same goes to poorer players, but because they grim trigger the richest players, the contributions drop, and then they again lose a lot. But what happens about the productive player with the productive players? So the most productive player gains less from deviating because their productivity of the endowment, so if they just keep the endowments to themselves, it's basically equal to 1, then the productivity in the social dilemma where it's some kind of R that is much greater than 1. So they have a lot to lose from this deviation. And basically, the optimal sharing rule balances these considerations, and inequality makes it easier to do so. So if we come back all the way from the example that I started with, the motivating example with the sharing rules, we can compare the qualitative behavior again. So basically, we see that for any of the rules, cooperation breaks at some point. And for optimal sharing, which corresponds to the heat map in the simplices, it can be sustained everywhere. And qualitatively, perhaps the proportional to endowment sharing is the closest to the optimal sharing in the way, because here the cooperation area goes up towards the more productive player as cooperation gets easier in optimal sharing as well towards the more productive player. but it is still breaking in some extreme inequalities, whereas optimal sharing can still sustain cooperation. So it is better in a way to share according to this rule than any other rule that we considered. So before I go further, do you have any questions? Okay. Then the next step, what we do is we would like to see if our observations and the equilibrium analysis correspond to what evolution tells us. To do so, we run some simulations, and for this we use the introspection dynamics, which is a stochastic dynamics, where players occasionally reconsider their current strategies. So there are payoffs for the new strategy and for the old strategy, and the players have to compare them, and there is a probability rho that can be calculated according to formula 8 that tells us basically with which probability the player will switch to the new strategy. So if selection strength S is very large, say goes to infinity, this basically comes down to the sign of the difference between the payoffs. So if the new strategy brings even slightly higher payoff, the player will switch with a very large probability. And if the new strategy yields a lower payoff, then the player will not switch and will stick with the old probability. So when we go into simulations and we run this for a number of generations 10 to the power 6, we can see that the behavior of the dynamics actually corresponds quite closely to what we observed in the heat maps that I showed you before. So if productivities of players are equal, and in this case it's 1.7, then equal sharing is struggling to sustain cooperation. There's a very low group payoff, meaning that cooperation is not very high. Whereas optimal sharing can sustain cooperation better at the corners of the simplex, and as closer we get to the center, the harder it gets for cooperation, and the lower the group payoff becomes. And similar observation is for the unequal productivities. So in this case, we see that player 1 is the most productive, and their productivity is quite high. So actually, in this graph, it's not so easy to see that the corners for player 2 and 3 are also filled with payoffs. It's just that their productivities are so low that it doesn't show the group payoff is not high enough. But cooperation does get a little bit easier as we go to the corners than it is in the middle of the simplex. And for the same parameters, equal sharing cannot sustain cooperation at all. So qualitatively, evolutionary dynamics seem to emulate this behavior of the constraints and the delta minimum surface that I showed you before. Questions? Okay, either I lost you all or it's all very clear. I will go now to the last part that I wanted to talk about if I have time, because I seem to have time still. So another implication of the model, and I already slightly hinted at it when I was talking about strategic incentives, is that what if players, instead of keeping endowment to themselves, can invest it in something else? What if there is a possibility for each player to do something to the endowments that they do not contribute? So here we call this outside options, but you can see it as just investment. Say each player has some project, an alternative project to the social dilemma, the team effort that they could contribute to, and there is some productivity to each of the projects, and these productivities say differ. So Qs now correspond to the productivities of the outside options. And now they have to decide whether to contribute to the individual project that they have, make these individual decisions, or to contribute to the public good and gain this profit according to the sharing rule that we have to define. So now we need to do the similar steps as before, but accounting for the possibility that players that do not contribute actually gain from outside options. And basically, if you see an equation 10, so we can find this F star hat in a similar manner using delta minimum. But now the productivity of the outside option Q is actually increasing the share of the player. So basically, each player now has to get more if their outside options are productive and if they're very attractive. So they have to be guaranteed a larger share. If this if these productivities are lower, then they might actually reconsider and instead be more see more attractive to contribute to the public good. But let's say only consider now the more productive outside options to see how this affects the corresponding feasibility areas. Yes, and also we can use the same mechanism with the metrics and eigenvalues to find the corresponding rule. So basically, we observe that homogeneous outside options make cooperation easier. And once one player gets some attractive options for the individual investments, then cooperation breaks down, especially in this area closer to the player where the player has a larger better outside option. However, even here, if we go far enough into the corner, if we give enough endowment to the player that has some outside option, they must still be willing to contribute to the social production. So in this sense, the qualitative prediction of the model is still similar, that inequality is still better for cooperation. It's just that it's skewed given the outside options of the players. And we can confirm this by also providing some, running some evolutionary simulations and observing that the dynamics also exhibits a similar behavior, that heterogeneous outside options make it harder for cooperation. And as we go further to the corners, we can still find this feasibility areas and players are willing to contribute. But once they're equal in the middle, it gets harder and cooperation breaks down. Right. So now going into conclusions, first, I would like to say a little bit about how we contribute or fit to the existing literature. So we know that generally in collective actions, individual effort increases with benefit cost ratios and endowments. And also without a social dilemma aspects, players contribute more as endowments get more unequal. So under optimal sharing, we do similar behavior, but in social dilemmas. So we basically, this optimal sharing helps to overcome the social dilemma problem. So if we can control the distribution of the allocation of the public good, then we can overcome this problematic effect of the social dilemma. And to summarize what we did in this project, first we derived an optimal sharing rule that can sustain full cooperation. And according to this rule, rich players get a larger and yet proportionally smaller share relative to their contributions. And endowment inequality makes cooperation easier, not harder. And also more productive players receive a smaller share, which might seem as an unfair effect, but it is rational. And thank you for listening.